Welcome back to this section of my tutorial. In this video, I'm going to take you through systems of equations and the different principles underlying it. So, generally, a system of equations can be represented as A multiplying X is equal to B, right? But before we start, if this is the first time you have been on this channel, kindly subscribe so you get updated whenever I upload our subsequent tutorials. So systems of equation, as I said, is represented as AX is equal to B. A here is defined as coefficient matrix. The coefficient matrix. Then the B is, should I say, let's say your right hand side values. Then X is what we call the unknowns. So now, the reason why we say systems of equation, you already know that an equation is any expression having the equal sign, right? Yeah, so if I have 2x plus y is equal to 1 or 0, this becomes an equation due to the presence of this equal sign. When we say systems of equation, it means that I have a series of this equation here. So I have, let's say, another one, 4x minus 2y is equal to 0, or let's say then I can only have 2 at this time because it's 2 variables. So this gives me systems of equation, right? So for systems of equation, it starts from 2 or more. You can have an equation which is only 1, right? So we're going to tackle equations which are maybe 2 or more. Let's say 3, 4, 5, 6, 7, right? So in real life, you're not going to have only 2 equations because whenever you want to model anything, the parameters in nature are many, so you're surely going to have, let's say, 5 or 6 variables. Let's consider somebody who is a civil engineer and analyzing a structure, right? So the different forces acting at the different joints wouldn't be only 2 variables, right? So you can have as many as 10 variables. So how do we solve these systems of equation? So that's why we apply the different methods such as the Gaussian elimination and the other iterative methods. So in this video, I'm going to enlighten you about systems of equations and some terms which are associated with it. So when you say AS equals B, as I said, being the general representation of systems of equation, A here is a coefficient matrix, right? So we are interested in finding the value of X. X is simply equal to A inverse multiplying B. This is a simple matrix operation. So meaning that to find the value of X, we should be able to find the inverse of A and you multiply it by what? Our B. So let me throw more light using this about the B. Using these two equations here, you realize that I'll have this as my left side and this as my right side of the equal sign. So this gives me my A. The coefficient here gives me my A. So my A here will simply be equal to the 2 by 2 matrix 2, 1, 4, negative 2, right? Then my B is simply equal to 1, 0. So that is the difference. So to get the values of our unknown X, we need to find the inverse of what? A, then multiply it by what? B. Is that not it? So the first takeaway is if a system has a solution, we call it a consistent system. We call it a consistent system, right? So a consistent system. So any system that has a solution is what we call a consistent system. Otherwise, it's inconsistent. Then, how do we determine that a system is consistent straight away? You can realize that to get a value of X, we only have to find the inverse of A. So meaning that the condition for a matrix to be consistent is the matrix should be invertible. The matrix should be invertible, right? So when you say invertible, it means that it has a determinant which is greater than 0, okay, it's non-singular. Let me say non-singular, right? So this is the definition for invertible. So any matrix, or sorry, any system of equations whose coefficient matrix is invertible is a consistent system. So take note. So if a system doesn't have solution, yes. So if a system is inconsistent, then the coefficient matrix A is what? Singular matrix, a singular matrix. Or you can say that it has a determinant of what? 0. So whenever the coefficient matrix after writing it gives a determinant of 0, it means that we can't find solution to the system, right? So take note of that. Then also, if a system is consistent, then it has some possibilities which you should take note of. So let's consider systems. Consistent systems. You realize that for consistent systems, yes, you can either have a unique solution, or infinitely many solutions. These are the only two possibilities for consistent systems. You realize that if it's inconsistent, it means obviously it has no solution, right? But for consistent systems, it also have either a unique solution or infinitely many solutions. So how do we know that it has unique, and how do we know that it has infinitely many solutions? So this is where we have a concept called the rank of a matrix. A rank of matrix, right? So when you say a rank is the number of independent rows, right? Or linearly independent, you can put linearly there. So number of independent rows in the matrix, that is the rank of the matrix. So once you've known that the rank of the matrix is number of linearly independent rows, we can go ahead to test for the consistency of the system. But how do we do that? Let me use an example here so you get what independent rows mean. Now, if I have a system, we've already done augmented matrix. So if you are not familiar, kindly subscribe, and also you get access to the previous lecture which was on augmented matrix. So here, let's say I have A, B, C, right? Then I have 0, 0, then I have D, E, 0, F as my coefficient matrix expressed as a triangular matrix. Then I have my B side here. So I'll have, let's say, 1, 1, 1. Let me say this is. So the entire system here is what we call augmented matrix. But this small portion, which is the 3 by 3 matrix, is what we call the coefficient matrix. So take note, we have coefficient matrix, then we have the entire being what? Augmented matrix. Augmented matrix. So in this case, whenever you have a system like this, because after simplification, you can never take away any of the entries again, or none of the entries here, which is the A, B, C, D, E, F, they can't be 0. It means that this row has what? A rank. Yes, because there's a non-zero entry here. So when you talk about let's say rank, we are only talking about the non-zero entries. Any row with a non-zero entry has a rank, yes. So assuming I had this F to be 0, meaning that I have a row where all the entries are 0, it means it's not part of the rank. No, I'm not talking about that. So when you talk about rank, a rank involves counting rows with non-zero entry, at least one non-zero entry, right? So let's say the F is here. So in this system, you can clearly see that my coefficient matrix has a rank of 3, because row 1, yes, row 2 and row 3 all do have at least one non-zero entry, right? Then when I consider the entire augmented matrix too, you realize that it's the same thing. Each row, when you consider the augmented matrix, the row becomes from here to this side, here to this side, here to this side. Also has at least a non-zero entry in each row and also has the rank as 3. So the conditions are whenever the rank of the coefficient matrix is equal to the rank of the augmented matrix, then your system will have a unique solution. Take note. Then your system will have a unique solution. So in basic terms, this is what we normally say, that if you have two unknowns, you should get two words equations. If you have three unknowns, you should get what? Three equations. So that's the implication. But mathematically, we say that if the rank of the augmented matrix is the same as the rank of the coefficient matrix, then our system is going to give us a unique solution. On the other hand, you realize that if I turn this f to 0, I'll have the rank of this coefficient matrix to be 2. But for the entire augmented matrix, because I have 1 here, I will get what? 3. So now you can see they are not equal, right? So since they are not equal and the augmented matrix has a higher rank, I'm going to have infinitely many solutions. Take note. Infinitely many solutions. Infinitely many solutions. So in terms of rank, if rank of the coefficient matrix, let me represent it as C, is equal to rank of the augmented matrix as A, then its unique solution. Or if the rank of the coefficient is less than rank of what? Our augmented matrix, then we get infinitely many solutions. On the other hand, you realize that if the rank of our augmented matrix is less than the rank of the coefficient matrix, then that one you have no solution. No solution. So these are the basic concepts you should understand in systems of equation before you start maybe doing numerical methods or numerical analysis. And even it's going to help you in your algebra. So thank you very much for being with me in this video. And please don't forget to like and share.